So how do you actually measure molecular polarity? What you do is you put your sample between electrically charged plates. A pair of electrically charged plates is what's called a capacitor. Okay? So you put your sample in there. So if one's end is positive, the other one's negative. Okay? Capacitor is something that can store a charge. So if you were to hook up like a capacitor to a battery, for example, okay. All right, so let me put a switch over here. So if I were to close this switch, what's going to happen? This is the negative end of the battery. That's the positive end of the battery. Okay. So if I were to close this switch, okay, electrons will have a tendency to flow from the negative end of the battery to the positive end. So electrons will flow this way. Okay. But then because of the gap here, right here between the two plates, okay, the current flow is just temporary. It will just flow for a little bit and then it will stop. So there's a limit to how much electrons can be stored over here. Okay, by putting a polar molecule in between these two plates, you can polar molecules between those two plates, you can actually increase the ability of your plates to store extra charge, to store electrons. Okay, so that's how you can measure polarity. We're not going to go into detail as to how that measurement is done. Just to give you an idea as to where that, I just want to give you an idea as to where that experimental measurement, how that experimental measurement can be made for dipole moment. Okay. If you want a better simulation of that, let's see a better picture of what's going on there. Let's go to phet.colorado.edu. There's a simulation there on molecular polarity right here. So if you run that simulation, you'll see okay. So if I turn on my electric field, I'm basically putting a charge. So this is now positive, this is now negative. Okay, so I'm hooking that up to a battery. And this is the positive end of the battery right here. Okay. And if I put a polar molecule in between those two charged plates, what happens is this. First of all, let's say right now, the way this is set up is my electronegativity for A is low, lower than that for B. So what do you notice? B is more electronegative, so electrons that are shared between A and B are polarized towards B. So we have that arrow pointing towards B. That's what the bond dipole arrow tells you. Okay? If I put the partial charges on, you can see that the partial negative symbol is written next to B. It's partial negative, partial positive. We say B is more electronegative than A. And the bond character we say is polar. Okay? So it's between pure covalent and pure. So on this side, it's more covalent. On this side, it's more ionic. It's somewhere in between. Okay, so polar covalent bond. I can actually show the electron density right here. And you'll notice it's a little darker. It's grayer on this side. Okay? On the B side than it is on the A side. All that is telling you is that there's a higher electron density around the B atom. We say B is more electronegative. What happens if I make A more electronegative than B? I drag this one over here. What do you notice? Ooh, what happened? I make A more electronegative, then what happens to A? It becomes partially negative charged, right? So the A now is partially negative. It's now attracted to the positive plate, positively charged electrical plate. Okay, and you can see this one's dark. The shading right here is darker. That means you have a higher electron density near atom A. Okay, now what happens if I were to turn this molecule? Oh, what happened? Right there. So your the A atom, the partially negative end of your molecule is attracted to the positively charged plane. Okay?